Okay, so I am recording after all. So with that being said, we're going to go through climate, severe weather, and wildfire. The study guide is fairly comprehensive. The one exception to that is I'll just say that there are a few very basic climate change questions that will be on the midterm. These climate change questions are not as detailed as what we see in the textbook. They're just very general questions about whether or not global temperatures are rising or falling, whether CO2 concentrations are rising and falling. And so there are a couple of questions on that. I realized when I was going through this review guide this morning that I had not included that previously. So for those of you who are studying for the midterm, just keep that in mind, that you will want to at least review your lecture notes for the discussion on climate change, at least briefly. So with that said, unless anybody has any questions, I'll start off with climate and weather processes. So one of the things that we need to recall is that if this actually changes, okay, so there we go. So climate versus weather. This is a very fundamental first order difference. I think that now that we've gone through the lectures on climate and weather, it's probably more apparent than it might have been at first. Climate is the average pattern of weather in a region over a long period in time. So, generally speaking, Southern California is warmer than Alaska. Seattle is wetter than Nevada. And so, within each of those regions, you might have short-term changes, which are weather related, but climate is referring to the overall patterns of weather over an extended period of time, whether something's warmer or colder, wetter or drier. Examples of changes in climate include the ice ages, multi-year droughts that can extend into decades in some instances, and the overall change in climate that we see to rising carbon dioxide and greenhouse gas levels. Examples of changes in weather are when we see thunderstorms, hurricanes, tornadoes, and whether or not the skies are shining or we have floods because of massive amounts of rain. Moving on to what drives both climate and weather, when we had talked about plate tectonics, we had talked about heat being the driver of all things related to plate tectonics. So heat is what drives the eruption of volcanoes. Heat is what drives plate tectonics moving at the surface, which causes earthquakes. The heat that we get from plate tectonics is derived from energy that is inside of the earth. And that heat is coming from a number of processes that occurred early on in the Earth's history. In contrast to that, the heat that drives the processes associated with climate and with the weather are heat that is coming from the Earth's exterior. In this case, it's solar energy. The way in which we receive energy from the sun, we actually have it coming over a range of wavelengths. So the radiation that we're receiving is both found within the visible spectrum. So we see light, and that light comes from the sun. But we also get energy that is both shorter or higher frequency, shorter wavelength, and longer wavelength radiation. And so the longer wavelength radiation is called infrared. And so that comes to us in the form of heat. And then ultraviolet light is shorter in total wavelength, and that comes to us as UV light. And so that's the sort of thing that will give you a sunburn. And the incoming sun, the solar energy from the sun, a number of things can happen to it as it makes its way towards the Earth's surface. 30% of the sun's energy is returned back to space as it's reflected and scattered. And the remainder, approximately 70%, is absorbed. And this absorption can come in a number of locations. So you have absorption by air molecules. A portion of it is absorbed by clouds. And a large portion of it, about half of it, is absorbed by the Earth's surface. And that's heating up the Earth's surface. And the surface is both on land and on water. And so the budget is approximately 70% absorbed, 30% reflected and scattered. This reflected and scattered portion, the reflectivity, is referred to as albedo. The albedo can change depending on the Earth's cloud cover and the Earth's the cover of ice and snow. And so during periods of time in which we've had more clouds or more snow, so during an ice age we have more snow and we have more ice, we'll actually see an increase in albedo, and this will further decrease the amount of heating that we see at the surface as things are being reflected off the surface. Now, the flip side of this is that the Earth and any body located within the solar system, within the galaxy, within the universe, it will also emit radiation. The difference between the Earth and the Sun is that the radiation that the Earth is emitting is longer in wavelength. It falls within the infrared portion of the spectrum, and this radiation is being radiated out as heat. The caveat to this, and this is something that we talked about with climate change, is that the amount of heat that is radiated back out to space depends in large part on the atmosphere and cloud cover. And so certain types of gas, greenhouse gases, are really good at absorbing this long wavelength radiation. And so we can actually cause the Earth to basically become further blanketed by increasing greenhouse gas levels. And this observation comes from looking at measurements of temperature at the surface versus measurements of temperature from outer space outside the atmosphere. And what we find is that the heat measured out in space, the temperature, is on average 3 degrees Fahrenheit. So if you take a satellite and put it up into orbit and it's measuring the Earth's surface temperature, you'll get a measurement of approximately 3 degrees Fahrenheit. However, when you actually measure the average temperature on the surface of the Earth, it's 59 degrees Fahrenheit. And what we're doing is we're blanketing the Earth with the atmosphere, with the greenhouse gases, and we're actually keeping in heat to make it seem warmer than it might appear to be to an outside observer. And so this is a very good thing. We do want greenhouse gases because they make the planet more habitable. But the flip side to that is that if we add too much, we will make the Earth too warm. And yeah, so somebody needs to mute themselves. It's just a little bit loud. So make sure I'm mute unless you're asking a question. Another important concept that should be studied for the midterm is the fact that the Earth is not heating to the same degree everywhere. And this is referred to as differential heating. So the sun's rays hit the surface of the Earth, but you'll notice that at the point, and this is the equator right here, if you imagine that the Earth the axis wasn't rotated at all, if it wasn't tilted at all, if it was going straight up and down, the center point of the Earth, which would be in an untilted Earth, the equator, in all situations, you would see that the sun's rays were most dense at the center point. And then as you move towards the North Pole and the South Pole, the sun's rays become more diffuse. There's less energy making its way up to the poles. So we have differential heating overall because the sun ray intensity is not the same everywhere. And so the equator is going to be warmer than the poles. But in addition to that, we have an Earth that has a tilted axis, and it spins or rotates, or it travels around the sun. And so the portion of the Earth that is closest to the sun is going to change throughout the year. And so this is what gives us our seasons. The winter solstice coincides with a period of time in which the northern hemisphere, that's north of the equator, is further away from the sun and it receives less sunlight, where the southern hemisphere is closer to the sun and receives more sunlight. And so that can also be seen right here, where the sun's rays are most intense just to the south of the equator. And you can see that actually the North Pole is more or less completely covered in darkness. And so during the winter solstice, the amount of sunlight that the northern portion of the Earth receives is very little. And that's why the days tend to be, or why the days are shorter even here in the wintertime than in the summertime. During the vernal and autumnal equinox, that's both the beginning of spring and the beginning of fall, the Earth is situated in a way in which the equator is the closest point to the sun, and both poles see an equal amount of sunlight and darkness. And then during the summer solstice, that's a period of time in which the northern hemisphere receives the most sunlight. The net result of both the changing seasons and the fact that the low latitudes, so regions near the equator, receive more sunlight than regions further away from the equator, means that there is a surplus of solar energy being not produced, but there's an abundance of solar radiation in the low latitudes, and there is a net negative amount of heat being applied in the northern and southern portions of the Earth. And so this is a plot which shows us latitude. So at 0 degrees latitude, you're at the equator. And then you can move to the left and you travel towards the North Pole. If you move to the right, you travel towards the South Pole. And then you have on the y-axis watts per square meter. And so this is just referring to the amount of heat that you have in a given location. And then it plots both the radiation that's being lost. So that's the infrared radiation that the Earth is giving off in the form of heat. And then the blue is the solar radiation that's being absorbed. And so in regions where we have more solar radiation, we're going to be absorbing more solar, or where we have more solar radiation, we're going to be absorbing some of it. And so you can see that at the lower latitudes, we have this abundance of heat, and in the higher latitudes, we have less heat available. And so what this does is it sets up a thermal gradient. And so you have an abundance of heat that wants to flow outwards, and so it will transfer heat to both the North Pole and the South Pole. And so this imbalance in heat is going to try to be, the Earth is trying to fix it through the transfer of heat, because the Earth wants to be in equilibrium. And so it wants to send this heat into a number of different places. And this is the thing that will drive our weather. This is the thing that drives our climate, is this attempt to try to transfer heat more equally throughout the globe. And so the way that the heat is transferred is done in a number of ways. We've talked about this a number of times now, but we can have convection, in which the energy is being transferred by the mass movement of particles or molecules. And so an example of this is if you had a boiling pot of water, as you see the bubbles rising up, you get little tiny currents within the water, and the actual water particles are moving and transferring heat that way. And so the hot water rises up, cools down, sinks, heats up, rises up, cools down, sinks. And the same process occurs in the Earth's mantle, which is convecting. This process occurs in the Earth's atmosphere, where we have hot air that is less dense and therefore rises. And as it rises, it cools, and it'll eventually sink. And so the actual particles of air are moving up and down according to their temperature and their density. Another way in which we get the transfer of heat is through radiation. Electromagnetic radiation is the same radiation that comes from the sun. And so this can be transferred in the infrared portion of the spectrum as heat. And then we get heat transfer through conduction. And this is being done in the case of a solid. So you have metal. And if you take the handle of a pot, at first, when you put a pot on the stove and you start to heat it up, the handle's cool to the touch. But if it sits there for enough time, or if you've ever made a mistake like I have, where you put a metal spoon into a pot and it sits there for a couple minutes, when you go to pick the spoon up, it's very hot. And the reason for this is that the particles within the spoon, although they can't move from one place to another, they can actually transfer the heat or the energy in the form of heat from one particle to the next. And so the individual particles will transfer the heat through the object. And so convection is an important process for transmitting heat throughout both the atmosphere and throughout the oceans. Conduction is a way that we can transfer heat in the ground, the solid ground. And then radiation is how we transfer heat from the sun to the earth. We're going to skip that because I covered it. In talking about climate and weather, we cannot forget about the importance of Earth's water and the fact that 71% of the Earth is covered by water. And the vast majority of this water is found in the oceans. So as the solar radiation is received by Earth, we want to be able to transport that heat throughout it. And a lot of that energy is going to be used to power the hydrologic cycle. And more generally, it's just a good way to be able to pick up that heat and carry it to another place. And that's because water has a very high heat capacity. So table 9.3 in your textbook talks about the heat capacity, which is the ability of a material to carry heat. And just plain old air doesn't have a very high heat capacity at all. In fact, it's orders of magnitude smaller than quartz, sand, and granite, which is basically a reasonable approximation for the Earth's surface, and water as well. And so if you want to carry heat with you, if you want to be able to transport it, locking up into water is a very smart choice. And it's not, it's not that the Earth is thinking this, but it's just the best way to transport that water. So the way that we transport heat and water is through phase changes. And we can either absorb heat or we can release it depending on where we are in this phase diagram. So for a pretty basic example, we talk about ice to water. And if we want to turn ice into water, we need to absorb heat. And the amount of heat that we absorb is listed here. And so this is 80 calories per gram, meaning that if we wanted to melt a larger quantity of ice, we would need to add additional heat. And so going from ice to water or water to ice requires us to either absorb heat or to release it. And the amount that we're releasing is fairly small, or the amount that we're absorbing is fairly small. Going from water to water vapor and back again requires significantly more heat, whether or not we're absorbing it or releasing it. So if we want to take water, if we want to turn it into a gas, which is water vapor, we need to absorb 600 calories per gram of heat. If we want to then take that water vapor and recondense it back into water, then the heat that needs to be released is 600 calories per gram. So you can imagine here that if we want to take heat and we want to transfer it to some other place on the planet, the way that we can do this most efficiently in terms of the amount of heat that we can carry, going from water to water vapor is the ideal process to do that. And this is what is powering our climate and our weather primarily, is this water to water vapor transition. And in our talks about severe weather, this is the process that typically dominates. This is the thing that's producing these thunderstorms that we talk about, produces tornadoes, produces hurricanes, is this water to water vapor and back again process. Moving on and talking a little bit about atmospheric layers, I would recommend that everybody has a good understanding of this figure, that they can point out all of the major layers. So the troposphere is the layer closest to the Earth, followed by the stratosphere and the mesosphere. And this is really only it's not the entire atmosphere. We have layers beyond it, but this is the portion that we're going to focus on for the midterm. This green line corresponds to the temperature profile throughout these three layers. With the troposphere, we run into a bit of a problem. And that's the fact that we have hot or warm, low density air sitting beneath air that is colder and more dense. because dense warm things want to rise, or warm light things want to rise while cold dense things want to sink, this creates a situation in which we get convective instability. So this portion of the atmosphere wants to move around. It wants to convect. It wants to move heat around to put it in the proper place, because it wants to make the nice warm things higher up and the cold dense things lower to the ground because they're heavier. And so this is what's powering the weather that we see at the surface of the Earth. The stratosphere is the opposite of the troposphere, in which we have cool, dense air sitting at the bottom and warm, light air rising to the top. And so the stratosphere is characterized by having clear, sunny weather. The mesosphere is actually fairly poorly understood, just because it's too high for us to be able to send up weather balloons, but we're not able to launch spacecraft to sit in the mesosphere either. And this is not something that will be something we worry about or in terms of climate or weather for the exam, although understanding where the mesosphere is relative to the stratosphere and troposphere is a possible question that could be asked in the midterm. The points where we have an inflection in the temperature profile and where we go from one layer to another layer is referred to as either the tropopause, if we're going from the troposphere to the stratosphere, or the stratopause, as we're going from the stratosphere to the mesosphere. To give you kind of an idea of what we're talking about in terms of elevations, a commercial jet will fly at about 10 to 11 kilometers. And things like Mount Everest are at about the same elevation, so we're talking about here. This is just, again, a reminder that the troposphere is where we see this unstable dynamic situation where we have the warm air and the cool air mixing. And this is where we find the majority of Earth's air, and the vast majority of the water vapor that's locked up in the atmosphere is found within the troposphere. And we're just going to skip that. Global air circulation, understanding why we have these convective cells in their name. So the Hadley cells are our low, our convective cells that are close to the equator. They are dominated by the warm, moist air that rises off the surface. And as it rises, it eventually cools and falls back down to Earth, where it then warms up again. These cells are then the mirror image of them is reflected in the feral cells, where you once again have the cool air that's sinking down at the Hadley cell also pulls down air this way. And so as the air descends, it starts to warm up, and then it eventually gets to the point where it's warmed up enough that it starts to rise, and so you get another circulation pattern. And the regions in which we see the cool air sinking, we tend to have drier air typically, because all of the water has condensed out into clouds and eventually rain. And so we see lots of rain at the equator. We tend to see drier conditions at the meeting place between the feral and the Hadley cells. And then we tend to see, again, more moisture being released at the intersection between the feral and the polar cells. But the convection of these cells, because these are very massive regions of air that are moving around, they're actually, the effective direction of them is affected by an apparent force that we call the Coriolis effect. The Coriolis effect, I think, is something that people often have a bit of trouble understanding, and so I'd suggest that you make sure you understand what the effect of the Coriolis effect has on air moving either to the north or the south of the equator. So if you have air that is north of the equator, what you'll see is you'll see a deflection to the right. So if something's traveling to the north, it will be deflected to the right, which is to the east. And then if you have air that's coming down from the north to the south, it again deflects right, but because you're looking at it coming from a different direction, you'll see it deflected to the west. And this is the same case, but in reverse for the South Pole. So if something is moving from the South Pole towards the equator, you can see it's deflected to the left. And then if it's moving from the equator to the South Pole, it's again deflected left, but you're going in the opposite direction. Understanding the Coriolis effect takes a bit of effort. The example that I showed in class is basically you start from an understanding that the distance that a point travels close to the pole relative to the distance a point travels on the equator is significantly different. They both make one complete rotation around the Earth in 24 hours, but a piece of land right here, let's say in like Ecuador, has to go a much further distance in that 24 hours than a point that's located in northern Canada. So the velocity, which is a function of distance over time, the time in both cases is the same. The distance in this case is larger. So the velocity in the case of something traveling near the equator is larger. So that's the first thing you need to remember, is that the velocities here are much larger than the velocities to the north. So we take a step back for a second and think about what happens when you try to score a goal, kicking a ball from one train to another train. If the trains are moving at two different speeds, what's going to happen is that you're not going to make the shot. The blue train is moving faster than the red train, so even though you're lined up at one point in time at time equals 0, let's say, with a net. So right here is time equals 0. You shoot the ball at some later point in time when the ball's supposed to hit the net, it's going to move to the right because the ball has a component of speed in the right direction because it's moving faster with the blue train than the red train, sorry. So if you try to do the same experiment on Earth where the trains are now stationary, but the blue train is moving faster than the red train in the sense of it's faster because the Earth right here is moving faster than here, you're going to run into the same problem. And so if you kick the ball to the north, the ball will look like it's going to the right. And if you kick the ball to the south, it'll look like it's moving to the left. And so that's what we see here, and that's where we get the Coriolis effect from. And so I would encourage you, I have an example here, but if this is something they're struggling with, I would spend 10 to 15 minutes just doing a little bit of Googling, and a lot of different people have taught the Coriolis effect in their courses, and so they have different tools that might make it a bit more understandable for you. So a very schematic view of global air circulation looks like this. This is a figure from your textbook. A few important notes are just regarding terminology and what an easterly and a westerly is. So easterly is a wind coming from the east and headed to the west. So you have wind starting off in the east and coming to the west, and so that's an easterly. If the wind is coming from the west and headed to the east, that is a westerly. And so the majority of the United States has winds that predominantly come from the west and move to the east. I don't think I have that. Let's see. There we go. This was that. I'm going to see if I can share this. So this is the example I showed in class yesterday. And so this is weather right now. And you can see that at the low latitude, so this is between 0 degrees and approximately 25 degrees, we get wind that is moving from the east to the west. And so these are easterlies. And those that are coming from south of the pole, or south of the equator, are coming from the east and moving towards the west, and they're both converging towards the equator. And so if you kind of just look at this region in here And then we flip back to the screen that we had previously. I know it's kind of hard to go between the two. You'll see that that actually lines up quite nicely. We have the convection that is occurring at the cell level. So we have the Hadley, the Ferrel, and the polar cells. And we also have currents of air that move at high speeds that are referred to as jet streams. And we have the polar jet and the subtropical jet. And these jet streams travel at very high speeds. They are fairly narrow conduits of wind, and they travel around the Earth. And they can have a large influence on weather. One of the things that we talk about with tornadoes is the influence that the high wind speeds associated with the jet stream have on the production of shear in the upper atmosphere that can then lead to tornado formation. Since we're, want to try to stay on time, we talked about cyclones and anticyclones, and cyclones are regions in which we have low pressure versus regions where we have high pressure. The understanding the direction in which winds travel for cyclones and anticyclones, and which way both at, if you have air sinking upwards or downwards. So in an anticyclone, the air is traveling down. As it travels down, it's warm. Well, it starts off as being cool, and then as it descends, it warms up, and it tends to be dry and bring dry conditions. In the northern hemisphere, this leads to a clockwise rotation pattern. Cyclones, in contrast, are regions in which we have rising air. The air, as it rises, it cools and condenses, and in many cases brings rainy weather. The direction of wind travel at the surface is counterclockwise. And so here we just have an example of a cyclone forming into potentially a hurricane. And we'll talk about that in a little bit more detail later. We also talk about weather in terms of air masses. So, we have these convective cells within the atmosphere, but what we see is that things tend to travel as a mass of air. And depending on where the air comes from will determine what the air actually the properties of the air, whether it's warm or cool, if it's high in moisture or low in moisture. And the weather that we see at the surface is in large part dictated by the movement of these air masses. So we talk a lot about the warm, moist air that comes off the Gulf. So this is the Gulf of Mexico. The water there is warm. And so when air rises from here and it moves on land, we see weather as a result, particularly as we have dry air that will come in from places like it's cold and dry from the Arctic that moves down into the Great Plains. And so this is a region of the country where we see a lot of severe weather, both tornadoes and thunderstorms, hail, because these converging air masses. And the boundary between two masses of air is referred to as a front. The fronts are where we see a lot of weather associated with, in our case, we see it associated with the meeting of the warm, moist air from the Gulf and the dry, cold air from the northern portion of the continent. And I just kind of want to flip back to that other screen that I was showing earlier with the weather map. And I showed this in class yesterday. So we see again the wind changing direction or traveling. If you go to precipitation, so for example, we have a mass of air that's moving through here. It's moving to the east. And then we have air that's kind of meeting it right here. And you can see that everything gets caught up. And then there's a cyclone that's forming right in there. And if you look at precipitation, the dark colors are regions where we have high precipitation amounts. So this is showing in total number of inches. And you can see where those two masses are meeting, you get a fair amount of precipitation. And so this is where we're generating we have a front. Two air masses are meeting right here, and they're producing potentially severe weather. And let's go back to PowerPoint now. Okay. So this is an example of a front. So we have a cold front and a warm front. And again, this is another thing I would suggest people make sure that they understand what's going on here. So in the case of a cold front, we have cold air that's moving in, and it rapidly pushes up the warm air. As the warm air ascends, it eventually cools. If moisture is present, you will produce clouds, and you can get significant weather in this case. On the other hand, we have a warm front. And in the case of the warm front, the warm air moves in, and as it moves in, you'll see a gradual increase in the warm air as it rises, but it tends not to rise as dramatically, and that's the case of the cold front. And these are just two cartoons showing you the direction of airflow as a result of a warm front and a cold front. And again, you can see a change in weather in both instances, but with a cold front, the uplift that's associated with the incoming mass of air will tend to produce bigger clouds, cumulus clouds that can form both rain showers or even in some cases thunderstorms. We touched on this very briefly, but topography plays a role in weather and in climate. So if the mountains are sitting there for millions of years, then obviously they're going to have an impact on weather or climate in a specific region over an extended period of time. So in the case of large mountain chains, such as the Sierra Nevada, you have moist air from the ocean, warm moist air that travels inland, and as it gets to the front of the mountains, it has to rise in order to make its way over it. And as it rises, it's going to cool, it's going to lose the ability for it to carry as much water as water vapor, and so it's going to condense and it's going to rain. And the result of this is that the rain will basically, the release of the water will be exhausted as it makes its way up to the mountain. And when it gets back down to the other side, the water will be gone, and you'll get dry, cool air that descends and eventually warms up. And you have a region in which we have a rain shadow where we get very little rain. We get desert conditions, and we can see that throughout much of the Southwest, and particularly in Nevada, where we have deserts in many instances. Kind of skipping this and just talking briefly about ocean circulation. We talked up until this point about sorry, somebody, can you mute your phone or your computer? Okay, good. So we talked about the atmosphere being able to transport heat through the water vapor, but we can also transport heat through the oceans, through ocean circulation. And this operates in a way that's very similar to convection at the surface. So we have air convection in the atmosphere, but we also have the convection of water within the oceans. The water tends to be warmer at the low latitudes because you're getting more sunlight, so you're getting more heat that's being absorbed into the water. And the surface circulation, so the top couple hundred meters of the Earth's oceans, the circulation is driven by wind. And so wind patterns will dictate the direction that the water flows. And this is reflected in this image right here, which is taken from the textbook. Deep ocean circulation, on the other hand, and the oceans are very deep. In some instances, they're 8,000 meters, 10,000 meters deep. Deep ocean circulation is density driven, and the density varies as a function of temperature, very similar to the Earth's atmosphere and the Earth's mantle. And it's also a function of salt content. So if you decrease temperature, you increase density. On the other hand, if you increase temperature, you're going to decrease density. And so the less dense, warmer water is going to want to rise. Cooler, more dense water is going to want to descend. changing salt content also changes whether or not the water will want to rise or descend. And so if you increase the salt content, you're going to increase the density. And so you're basically adding more and more salt to the water. That's going to increase the density of the water, and that water is going to want to sink. On the other hand, if you decrease the density by decreasing the amount of salt there, then that water is going to want to rise. And so these two processes these two properties of temperature and salt content will affect the global circulation patterns of the ocean, in particular the deep ocean. And so the scientists have a pretty good understanding of global circulation patterns with the cold and salty water of the deep ocean that circulates and eventually will warm up and in some instances become less salty and will rise. Or you have warm, low salt content water that eventually gains salt or gains or loses temperature, and it will sink. There are some pretty important patterns of ocean circulation that vary from time to time. In affect Southern California in particular, and that's periods in which we see changes in the trade winds that will either enhance or decrease the temperature of ocean water off the coast of North America and South America. And so this is referred to as El Nino and La Nina, El Nino and La Nina. The normal case of wind patterns and ocean circulation have moderate to strong trade winds that push warm water away from the coast of North America and South America and push that water further to the west, so that you have a warm pool of water that extends to fairly great depths in the West Pacific. And so this is, you have Japan here, you have Australia here, Papua New Guinea and New Zealand, and so you get warmer water over to the side of the Pacific relative to this side. Now, if you have a time in which the trade winds effectively diminish or very weak, the imbalance of warm air diminishes, and so you get an increase in warm air or warm water to the east. And this warm water then is picked up, and you get enhanced rainfall in places like Southern California and South America. And it tends to be drier in Australia and in China. On the flip side, if you have periods of time where you have trade winds in which the overall pattern is enhanced, then the warm pool of water gets pushed even further to the west. It becomes extra cold over here, and we see less moisture being picked up in the clouds, and we get less rainfall. And this happens in both North America and in South America. And this contrasts with Australia and in China and in Asia, where you see enhanced rainfall in those in periods of time where we have a La Nina pattern of weather. So that basically does it for climate. I feel like I spent maybe a little bit too much on that. So we're going to go on to severe weather briefly. Let me now share the screen for that. Okay, so with severe weather, we start from the premise that we've just been talking about, which is we have imbalance of heat on Earth. And so that imbalance is rectified through transporting heat to the north and the south as water vapor in the clouds. And eventually that will cool and will release heat as water condenses and falls to the surface. And so this transportation of heat is what's powering severe weather. Okay, so this is a figure that just underscores this idea of where we tend to see the most severe weather in the United States. And this is a map showing thunderstorm frequency, and you can see that we have thunderstorms activity is the greatest in the southeast into the central plains, and this right here is a function of the fact that we have a frequent meeting of cold air and warm moist air. And so we have warm moist air that comes in off the Gulf and moves inland, and at the same time we have the cold dry air coming from Canada that moves down to the south, and a front will form often in this region of the country, and that front will produce upwelling warm moist air that will then produce clouds, and in some cases supercells, and we get thunderstorms, we get lightning, we get hail, and we get tornadoes. And that's why we see so much activity in this part of the country. And I'm just going to ask a reminder for people to turn off their microphones if they haven't. Looks like Dylan's on it. Thanks. So the stages of thunderstorm development, I would recommend watching the video again if you haven't, and then also referring to the textbook. So this is figure 10.12, and this really understanding this figure will help you a lot with understanding thunderstorms, tornadoes, and to a certain extent hurricanes. So in the beginning stages of a thunderstorm development, we have warm, humid air that rises. And this rising creates updrafts. And we'll eventually get the formation of clouds. These are typically cumulus clouds. So these are the white, puffy, cotton ball type clouds that we get that, might be passing through on a nice day. But as the updrafts continue, we also see air that begins to cool, water condenses, you form the clouds, and you'll get air that begins to sink. And eventually, if there's enough energy in the system, so you have to recall that as you're condensing out the air, you're releasing heat. And so as you release the heat, you're going to be able to turn more water into water vapor again. And so this is a positive feedback. And so if you have enough energy in the system, then what you should expect to see is an enhancement of the cloud development. It will continue to grow upwards. And if the system is set up just right, you'll get both updrafts and downdrafts that don't interfere with each other, but actually operate in a way that can actually enhance the development of a storm. And so this stage right here is referred to as the mature stage, and we will see in some instances severe weather as a result. We'll get the anvil-shaped clouds, we'll get heavy rain, thunder and lightning. Hail is a potential result. If it forms a supercell, we'll also see potentially tornadoes. And then eventually the energy in the system diminishes, and we're left with a period of time in which we no longer get warm, humid air rising and producing updrafts, and instead we see a system in which we are getting downdrafts, which dominate. The cloud mass will eventually shrink. We'll still see precipitation, but it tends to be lighter, and the overall energy of the system is diminishing. And this is just a couple images of the process. Again, understanding the fact that the way that this system can evolve, particularly if we have a mature, large thunderstorm, is if we have enough heat in the system to keep cycling between this water vapor, where we're releasing and absorbing large amounts of heat. And this is just an example of an anvil-shaped cloud. You can see in the mature stage, the top of the cloud has hit the bottom of the stratosphere. This is at the tropopause. And above this, we should see clear weather because we no longer have a thermal inversion where the cooler temperatures and the warmer temperatures are out of sync with each other. So I would look at this figure. So I'm working on the newest edition of the textbook, but this should be in chapter 10. I have figure 10.15, but this might be a figure number off. And this is differentiating a single cell thunderstorm from a supercell. The single cell thunderstorm, the warm air is rising vertically, and the cool air, the downdrafts also will descend relatively vertically. And the predominant form of precipitation comes out as rain or possibly hail. However, if we have the right conditions, in particular, we have a very strong system where there's a lot of energy to have these sustained updrafts and downdrafts, but we also get wind shear at the higher altitudes, we can actually get the formation of a supercell. And so the wind shear will produce a strong updraft and will tilt the overall system, and we get this anvil shape. And we can see light rain that kind of extends out from the edges, but then we also see heavy rain, hail, and then at the trailing end of a supercell, we can also see the formation of tornadoes. And so this is the sort of system that we need in order to produce a tornado, whereas with a single-celled system, we would not expect to see tornadoes. I'm going to skip through this again in the interest of time because I want to make sure we get to fires as well. But understanding that the types of precipitation that we might expect to see, whether or not we see snow, rain, freezing rain, sleet, or hail depends in large part on temperatures, both at the surface and within the atmosphere at higher altitudes. The formation of hail is a particularly interesting case because you have to be able to hold up blocks of ice. And I mean, ice has significant weight to it. Large hail can do significant damage to property. It can hurt people. And so it's something that, if you think about it, being able to hold up these large chunks of hail requires a lot of energy. And so the systems in which we see hail form tend to be times when we have a lot of heat energy present. And so the process of actually forming hail, we have raindrops that are brought up in an updraft. They eventually freeze. The hail will then eventually fall because it's brought down in a downdraft. And you'll get a little bit of melting, but you'll still have a frozen core, and the water will then accrete to the hail drop. It'll be brought back up, and it can grow from something very small to something very large. And so this is showing a cross-section in how large hail can grow. So you start off with a small little, what they call is an embryo. And then with time, it can get larger and larger. So this is not just falling down to earth. This is a process that's occurring as a cycle. And the hailstone will grow until it reaches a maximum size, depending on the energy in the system, and it'll fall back to the surface of the earth. And so this is an example of a hailstone that's grown to be 6 centimeters across, which is fairly significant and something I would not want to be hit with on the head. Again, we tend to see hail in places where we have the warm, moist air from the Gulf and the cool, dry air from Canada coming together. And we see a lot of thunderstorm activity in this part of the country as a result. And so we also see hailstorms. Another effect of thunderstorm activity is the production of lightning. The reason we get lightning is because of the updrafts and the downdrafts that are taking place within the system. You can kind of think of it in a way similar to walking your feet across the carpet. The rubbing of particles back and forth as they're either lifted up or brought down produces a buildup of charge. And so the negative charges tend to accumulate in the bottom portion of the the thunderstorm cell, whereas the positive charges dominate at the upper portions of the thunderstorm cell. And so the negative charges down at the bottom will actually induce a positive charge in the ground nearest it. And so this positive charge will build up. You have a negative charge that builds up at the bottom of the cloud. And you'll actually get, with time, both the leader, which comes down from the surface, and streamers, which come up or comes down from the cloud, and then streamers that will come up. And so they'll eventually kind of just seek each other out. And when the two are able to actually meet, you actually get a lightning strike or a lightning bolt. And so this process is somewhat random, and it's important to take cover in the event of an electrical storm in which we have lightning. Standing out in an open field makes you an excellent target for a lightning strike, in large part because you reduce the size of the gap between the surface with a positive charge and the clouds in which we have the negative charge. Likewise, standing underneath a tree is not a smart option, in part because that tree is going to become the object of the completion of that circuit. And if you're standing near that tree, there's going to be enough energy being released in the lightning strike in order to also hurt you. And so this is just showing the formation of the lightning strike from the initiation to the completion. And so we have the initiation of the negatively charged particles within the cloud. They produce the stepped leader. And then you have streamers at the surface, so you can kind of see these small little things. And at some point, a connection will be made. And at the point of connection, you'll get a completed circuit. So thinking about this as in terms of like turning on a light switch, and you'll get the electrical flow throughout the entire system. Jumping forward to tornadoes, again, we see tornadoes when we form supercells. We're not going to see a tornado with every single supercell development, but if we have the development of supercell, this is where it's going to be most likely to occur. The tornado forms on the trailing edge of the supercell after we've seen rain and potentially hail. And it forms because we have a number of processes that are operating. So we have the strong updrafts and then the displaced downdrafts. We also have winds at both mid-latitudes and then at high altitudes, including the jet stream, which take that updrafting air and shear it. And so as you shear this updraft, what you actually get is you'll get a rotation develop. And if there's enough energy there from updrafting warm air and the movement of air through the jet stream, you'll actually produce a pattern of circulation that will then generate tornadoes. And so we see tornadoes most commonly, again, in a region of the country where we have the warm Gulf air meeting the cold, dry air from the north. We have very strong fronts that develop, and we get tornadoes in what we call Tornado Alley, which extends from northern Texas through to Oklahoma and Kansas. And this is just a diagram of the formation of the tornado. I would recommend that people review the table 10.2 in the textbook, the difference between the Fujita and the enhanced Fujita scales. And you can see the differences within the table, understanding that the enhanced scale actually provides a bit more detail as to wind speeds, and we see that the minimum miles per hour is actually lower here than in here. Overall, they're similar, but there are some subtle differences, and you can see that we have both the description in terms of miles per hour, but we also have a description in terms of the types of damage that we might expect to see. Now, hurricanes are found in regions where we have the warmest ocean water. And so again, coming back to this idea that heat is the primary driver of weather. And so the places where we have the most heat, we have the warmest water, and we have the formation of hurricanes. And so hurricanes are sustained through warm water. So these are surface circulation patterns. And you can see that there's actually pretty good agreement between regions where we have warm water, shown with the red arrows, and the formation of hurricanes, and the direction of the two are also similar. So we have a lot of hurricanes that form off of the coast of Africa, and they travel, at low latitudes, and they are able to sustain themselves through all this warm, moist water, or warm water. As they eventually travel to the north around the Bermuda High, they lose power either as they travel over land where you have no water to further sustain the hurricane, or you get to a point where the water temperature cools off and you don't have as much energy in the system. Where you are on the globe dictates what you call a hurricane. The cyclones that we see off the coast of Africa and the mid-Atlantic are referred to as hurricanes. If you are living in Asia or Australia, we refer to them as typhoons, and they're referred to as cyclones in the Indian Ocean. But they're all the same thing, in which we have the formation of bands of thunderstorms that are organized and rotate around an eye. The eye wall region and the area surrounding the eye, but not the eye itself, is an area in which we get a lot of updraft. And this updraft rotates. And we see in this area along the eye wall, we see very high winds. We see the highest winds associated with the hurricane. Within the center of the hurricane, the very center at the eye, we actually will get cool downdrafting air. It will be dry. And this is an area where wind speeds are low. This is the area of the hurricane where if it's a very well-formed hurricane, you'd have severe weather passing through if you were standing on land, and then all of a sudden the clouds would disappear. You'd have clear skies, and you would think that all was well until the second eye wall passes through and you were thrust back into the hurricane itself. The damage and the intensity of a hurricane is measured by the Saffir-Simpson scale. The category is related to the pressure, wind speed, and storm surge, and the damage associated with each of these varies from minimal to catastrophic. So Dylan, sorry, I'm just going to stop for a second. What one should we pay more attention to? Is this in reference to the tornado scale? Yes, I would say the enhanced, but you should know the differences between the two. I wouldn't say that you need to memorize all of the numbers precisely, but having a general sense for, is an EF4 more dangerous than EF1 is important, and kind of having a sense for what the sort of the damage associated with each is, and a ballpark number for the wind speeds. So you don't need to have a number memorized down to the mile per hour, but having a sense that, if we just jump back for a minute. So for an EF5, you're talking 200 miles per hour, but an EF1, you're talking about 100 miles per hour, just kind of order of magnitude sort of thing, would be sufficient for the midterm. So the wind speeds associated with each of the hurricanes are likewise, just the ballpark. If you're a category 1, you're talking speeds of less than 100 miles per hour versus a category 5, wind speeds are going to be in excess of 150 miles per hour. I would also say that with the hurricanes, we don't have a figure on it, but also being able to understand that, prior to having a hurricane form, we have a tropical disturbance that can turn into a tropical depression that is a tropical storm, and each of these have increasing intensity in terms of further decreases in their pressure, increase in wind speed. The storm surge is an important aspect to a hurricane, in large part because this is what will affect people who are living on land. And the storm surge is not something that is necessarily the same everywhere, and it is affected by the speed of the hurricane and the speed of the wind within the hurricane. And so this is an example taken from the textbook, which shows, we have a storm that's moving. So the actual motion of the storm as a whole is 20 miles per hour to the northwest. The wind speeds within the hurricane are 100 miles per hour. And so when you have wind traveling along this side of the hurricane, since it's rotating counterclockwise, there's going to be an additive effect between the wind speed and the storm motion. And so the effective speed of the air at this point is going to be 120 miles per hour. On the other side of the hurricane, so again, the wind is traveling counterclockwise. So the wind is moving further away from land, and it's combined with the storm motion overall. You see effective wind speeds of 80 miles per hour. So what happens is that as the storm makes landfall, the surge height will vary. And so we'll see a larger storm surge, greater storm surge heights to the right of the midline of the hurricane, or the eye of the hurricane. So if you drew a line like this, that line corresponds to this line right here. And so the storm surge is going to be larger here than it is on this side. And so you're going to see variations in the intensity of the storm surge depending on where you are on the coast and where the hurricane makes landfall. The effect of the Bermuda High, which is a region of high pressure in the Atlantic, affects the path of the hurricane. And so we tend to see hurricanes that form off the coast of Africa. They tend to move westward, and then they'll move to the north, and they'll be unable to sort of come off in this direction and cross the Bermuda High because that region of high pressure is forcing everything around it. El Nino, again, we've talked about El Nino changing the weather patterns in California and Australia, whether or not you see more rain or less rain. But the presence of El Nino or La Nina can also affect hurricane patterns, which affect the east coast of the United States primarily. And so in times where we have El Nino present in the Pacific, we'll see cooler sea surface temperatures over here in the Atlantic, drier summers, and this will produce fewer Atlantic hurricanes. In contrast, when El Nino is absent, you'll see warm sea surface temperatures in Atlantic as well, and we'll get enhanced hurricane formation in the Atlantic. Climate change, I'm going to skip for the most part. The only things I really expect people to know about climate change, other than the fact that I think it's an important thing that we should all be aware of, but for the exam, global average and ocean temperatures have been increasing since the Industrial Revolution. This increase has been well documented globally, and the increase in the temperature has been well correlated with the increase in atmospheric CO2. So CO2 is a greenhouse gas, and if we go back to our climate lecture, we'll recall that the greenhouse gases trap infrared heat that's being emitted from the Earth, and it warms up the planet. And so those are the two key concepts that we need to keep in mind in terms of climate change. And I'm not going to require people to have memorized anything beyond that. And also, just as a point of reference, again, the vast majority of science being published nowadays is showing that global warming is happening and that humans are responsible for it. So I'm going to switch over to our lecture on wildfire. And I think that I'll actually just skip over to I guess I'll start with this one. Share screen. There we go. Okay, and we'll skip over the announcements, maybe. Okay. Again, just like with the previous midterm, you don't need to have memorized the details of the case study, in this case of the station fire, but I would encourage you to understand why the warm temperatures, low humidity, and dense vegetation all played a role in enhancing the wildfire here, and why those all play a role in more generally in terms of producing larger wildfires. So key concept number one, combustion is the reverse of photosynthesis. Photosynthesis is what generates plant material, produces oxygen that goes back into the atmosphere. It's powered through sunlight, which is the source of energy that's needed to combine carbon dioxide and water to produce plant material and oxygen. Combustion is the reverse of this process, where you're able to take plant material, and if you have oxygen, so this is a fuel that's in, this is the fuel for a fire, but you need oxygen for fire as well. Heating these two things up, you can produce carbon dioxide, water, and you'll also get energy back out in the form of fire. The process by which we remove and replace carbon in the atmosphere and put it in plants, this is referred to as the carbon cycle, and this is a very schematic version of the carbon cycle. But two ways that we can take and remove the carbon that's originally stored in plants and put it back into the atmosphere is through decomposition and combustion. And so in this case, we're focusing on combustion. Understanding regions in which combustion plays an important role comes back to productivity, so how quickly plant matter is being produced and how quickly that plant matter can be removed from the system. And so in some places like rainforests, we have a lot of plant production, but we also have a lot of microbial activity that can remove the plant material through decomposition. Deserts are the other end member, where we have very low productivity because we have very little moisture to begin with, so plants need the water to grow and they don't have it, so they will grow slowly. But because we have very little plant material, we don't have to worry about getting rid of it. The system isn't overrun with plants. California is an instance where we have periods of high productivity, such as in the winter months, coupled with a time of low productivity and an inability to remove the plant material through decomposition. And so fire is an efficient way to get rid of dead plant matter or an overabundance of plant matter. And so plants in places like the Mediterranean and Southern California have actually adapted to this sort of environment. And as a result, they rely on fire in order to, in some instances, reproduce, in order to keep their the forest ecology healthy. And so fire is a natural process that we need in order to maintain balance to the system in particular. The ingredients needed for fire are, we need fuel, and we'll need heat, and we need oxygen. Oxygen is, in abundance. It has been for periods of millions and millions of years. And so getting the fuel we need from plant material is something that will have a large influence on the type, extent, duration of wildfires. Thinking about ignition, I didn't really review this last time. We talked about it last week. The ignition is the activation energy required to light the fire. So we have fuel and oxygen sitting around all the time. It's not like plants are spontaneously combusting. You need some sort of initial energy input in order to get the reaction started. The two are not going to spontaneously react. So ignition is the key in this case. And so this is a map of lightning strike density throughout the not just the United States, throughout the globe. We again see lots of lightning in this part of the country because the cold fronts that move through and produce thunderstorms. And that's also reflected in here. But as you can see, the correlation between lightning and wildfires is actually quite weak in the United States. So lightning is a natural source of ignition for wildfires, but a lot of our wildfires happen out west, and there's a couple of reasons for that. It's very dry out here, so it's easy to start fires. And also because a lot of wildfires are the result of human causes. Arson makes up a quarter of all human cases, or all cases of wildfires, but we have a lot of accidental sources of ignition caused by humans as well. And so this map reflects the fact that we're not just seeing the wildfires being started by lightning. The wildfires spread in a number of different ways. So focusing first on glowing and flaming combustion, we see here the stages of fire being basically shown in cartoon form, and then we actually see real cases on the right. The front line of the fire is shown in here in this figure. Actually, that's a trailing side. I lie. So here we go. Here's flaming combustion on the leading end. And we'll see flames in this case. So flaming combustion we have, well, I think many of us think of as the typical sort of fire production. But then we also get combustion in a more steady state, glowing sort of way. And so this is cases where you still have combustion occurring. And that's important to remember, is the combustion is occurring, but it's not occurring in flame form, but rather it's slowly combusting and burning up material. And the majority of fires that we see look actually something like this. So we have the front of the flaming combustion. This is unburned material in here. And then we have a lot of material that's been burned in here, but it hasn't been burned 100%. And so the glowing combustion will go in, and there'll be continued combustion through this slower, more steady state process. The spreading of fire is something I'm actually going to flip to the next PowerPoint, because I think that actually shows it slightly better. Here we go. I'm going to go back a bit. Sorry. Trying to go backwards here. Okay, so fuel type. The textbook talks about different types of fuel. I've mentioned chaparral a number of times, that these are shrub-like plants, and not all shrubs and not all places have designed or evolved in a way to take advantage of wildfire, but in many cases they have. Shrubs and grasses in particular are something that we shouldn't underestimate when it comes to wildfires, because wildfire can travel quickly, and in some cases the shrubs have lots of oil in them that can make the plants very combustible. But they sort of act as a in-between to larger trees. So if you can imagine, if you just had a forest of large trees and nothing else, it would be very hard to light them on fire, and it would be very hard for the fire to move from tree to tree. If you have a number of different fuel types, including grasses and shrubs in a location, you can imagine it's easier for the wildfire to propagate in those cases, and it's able to travel quite well between the low understory and the branches of the trees. We also have structures which can burn, and it's not, I think when we think about wildfires, we tend not to think about houses as being a part of the problem, but in some cases they can be. And there's actually anecdotes in which a fire might have been fairly well contained, then a house catches fire, and then it just really restarted the fire as a whole, and made things a lot more difficult for firefighters to get under control. The propagation of fire is dependent on, in large part, on wind. The absence of wind tends to produce a simpler type of fire propagation, in which you have a column that travels upward as the heat rises, and the spreading rates of such a fire tend to be low to moderate in speed. When we have strong winds, the dynamics become more complicated. The fire tends to spread more quickly, and you can have interesting things that can result from such a fire, such as fire tornadoes. If the winds are strongest at the uppermost levels, so if you don't have strong winds close to the surface but strong winds further up, what you'll get material that can travel and actually be offset from the main body of the fire itself. And so this diagram of type 4 fire propagation is when we have strong upper winds and we have embers that actually spread the fire. So these burning embers fall back to the surface, and if they're large enough, they've been carried far enough ahead, they'll actually spread the fire that way. Very strong winds, Santa Ana winds, will spread fires very rapidly. These winds are the result of high pressure air masses that descend to lower elevations and bring with them dry air, often warm dry air. So this is a desert or it's effectively desert, where you bring in this warm dry air that will stoke the fire very easily. So it will help to make the fires travel very rapidly. And these fires can be very large, and they can be catastrophic. And so this is an example. Recall that we should expect to see winds that are moving from the west to the east. So winds should be moving onshore, and they should be bringing warm, moist, or not super warm. They should be bringing moist air on land. In the case of Santa Ana winds, you're going to be displacing that moist air with dry air, and it's going to be often warm dry air, and you're moving it in the opposite direction, and that will enhance the fires. And then you'll see clouds of smoke that then travel offshore. In a period of normal wind motion, you would see smoke clouds traveling in the opposite direction. The effect of topography has important implications for fire propagation. I've mentioned twice now that depending on whether or not you have a south-facing or a north-facing slope will affect the types of plants that will grow there and the density of vegetation. And both of these things will have an impact on how quickly fire can propagate through an area, or how it will spread. Where the most fuel is, where things are the driest, will impact the direction of propagation. And that more generally, fire travels uphill because heat rises and it's going to dry out the plants above it, and so the fire will then propagate in that direction. The reason that fires ultimately end is predicated on a number of circumstances. Part of that is whether or not the fires really get started and get going to begin with. How much fuel do you have? If you have some fuel, the fire can burn for a period of time. If for some reason you come to a stand that has been previously burned, you might not have enough fuel in order to continue the fire. And so sometimes fires will burn out just because the fuel isn't there for them to continue to propagate. Fires burn out because of changes in weather. The addition of moisture, whether there's just a lot of clouds, cooler weather that has higher humidity, or if you actually have rainfall, this can greatly impact whether or not the fire will continue or die. And then we also have the role of humans in fire suppression. We have cases where we can dump water, add moisture to a fire. We can actually coat the fuel, so the plant material, in chemicals that will prevent combustion. We can actually use fire to fight fires. We talk about backfires. And so we effectively burn the material ahead of the wildfire before it can get to it. And so then we create a space where there shouldn't be any plant material remaining. And then we can actually use mechanical means to create a gap in the vegetation so the fire can't jump across it. And so we use, axes, chainsaws, we can use, construction equipment to create a space where we don't have any fuel, and hopefully the fire will not travel beyond that line. And so this is an example of a fire break that was created. The ecology of fires is important. I've said several times now that fire is a natural process, and that this is something that periodically happens. The fire cycle in Southern California is approximately every 50 years. We should expect to see a fire. The plants and the forests have adapted to this cycle, and it's perfectly natural. The forests recover quickly after a fire. So this is 6 years after fire. Things still look fairly barren, but within 25 years, things are more or less back to normal. Some plants rely on fire in order to establish new seedlings, to grow new plants. They rely on it in a number of different ways, and different plants have different mechanisms in place in order to use fire to their advantage. Once again, the effects of El Nino and La Nina on the frequency and the severity of fires, wildfires, has been observed, and there's a correlation in times in which we have El Nino, which is enhanced, moisture in Southern California. We tend to see fewer wildfires in Southern California, and that's in contrast to places like Australia, where you should see an uptick in wildfire activity. In the case where we have La Nina, things are extra dry in North America, so we tend to see more wildfires. Whereas in Australia, the water is warmer, and so we get more thunderstorm activity. We get more moisture being falling in Australia, and so we see fewer wildfires in that case. So humans and fire. This is the thing we're going to end with. If you have any questions afterwards, I'd be happy to take them. Somebody asked if this video will be posted on YouTube later, and it will be. I have a meeting from 12 to 1, but when I get back from that meeting, I'll immediately upload this to YouTube and then post the link on Canvas. So the reason houses burn, there's two reasons primarily. The first is location. The second is home design. Location refers to the fact that houses in cities and in suburbs that have barriers between themselves and the forest are going to be less likely to burn. Whereas houses that are sitting in the forest surrounded by trees, plants in general, are going to be more likely to burn in the event of a wildfire. The other reason I said before is because of home design. And so there are a number of different things that affect whether or not a house is more prone to being destroyed during a wildfire, or at least catching fire down during a wildfire. Again, whether or not you're upslope affects the ability for a house to burn. So if you have topography and the house is situated at the top of the hill, that fire is going to travel uphill. You're going to get heating from the fire as it's making its way up. You can get, embers spreading, and ultimately this fire will make its way up the hill rapidly, and the house is maybe more likely to burn because of that. Building a house out of wood is a good way to make your house burn. You're building it with the same materials that are growing around you. The houses that are produced from masonry and concrete, ceramic, tile roofs will be less likely to burn because they just don't reach their burning point, or they don't combust as readily as the materials derived from trees. The wooden porch is another example. So again, it's made of wood. You can imagine if it's overhanging a hill, as the flames come up underneath it, it will be easily burned. The roofing material, again, wooden shingles versus ceramic tiles. Ceramic tiles are going to be significantly safer in the event of a fire. They might get damaged, but they're certainly not going to further spread the fire like wooden shingles would. Things like overhanging trees, keeping a roof clear of flammable material is an important thing to do. So you can see this tree right here. You can imagine that the amount of debris that gets accumulated on top of the roof will have a significant impact on the roof's ability to catch fire. Likewise, the fact that the tree is so close to the roof means that the fire won't have much trouble jumping from the tree itself to the roof. Planting bushes and shrubs too close to your house can be a problem, again, because the proximity between the two will allow for the fire to jump from one place to another. And so this right here is an example of, a good home design. You can see that there's forest off in the distance, but you have a pretty large green space between the forest and the house where you have no plants. The material near the house is definitely not flammable. You can see that they have rocks and they have some pea gravel, and it looks like their house is made of bricks. And so these are all design features that will help to mitigate the chances of a wildfire burning down their house. This house, in contrast, you can see that there are a lot of plants nearby. You can see it looks like there's a wooden structure right there, and this can be a problem. Window design. If you have a window facing downhill, you can imagine that would be more likely to be impacted by a fire as it traveled uphill. If you don't have the right type of glass installed, it will be more likely to break during a wildfire. And then if the wildfire can get through the glass and into the house, then at that point, you have a lot of materials within your home that are likely easy to combust. This is just, in general, more wood-based products, so a lot of louvers, shutters, both on the windows and on ventilation things within the roof can all easily burn. And so finding materials that are fire-resistant are important. And then chimney spark arrestor, preventing fires from starting from your chimney. And finally, making sure that fire crews can access your home in the event of a fire. Making sure the driveway is large enough that the grade, so the steepness of the driveway entrance isn't too difficult for a fire truck to make its way up. This is an example of a good versus bad design. Again, it's amazing the difference that you see between two houses. Here we have a plant material that is able to store a lot of water. These are succulents. These will be difficult to burn. They certainly won't be highly combustible, highly flammable. And so you can imagine the chances that you're going to have a massive fire coming off of these is very slim. This contrasts to this, which looks like it's just basically ready to go up in flames. Like if you look at it funny, couple that with the fact that both properties are located on a hill, so the fire is going to travel up, but you can imagine the fire is going to travel up here very quickly because of all the material it has to burn. The flames are going to be large. It's going to be easy for it to then find this wooden porch that's overhanging the slope, burn this porch up. Depending on what their yard looks like, the flames have then reached the front door. With the good design, even if this plant material were able to burn, it would get to the concrete wall, which is a natural fire barrier. It's a poor conductor. It will not combust easily. You will not have large flames as a result. And so this house back here is being protected by this wall as well, and you have no wooden porch overhanging it to act as an additional source of fuel. I'm going to skip this part of the lecture. There are going to be no questions about the total cost. This is more for people to understand that there are a range of options in terms of remediation. So remediation is the idea that we fix problems, we mitigate the chances of wildfire negatively impacting our home. And the idea here is that the options for mitigation range from free, in the sense that you might have to put in some blood, sweat, and tears, but the cost of materials is minimal. You don't necessarily need to hire somebody to do it for you, all the way up to very expensive. And these are things that you should think about when you go out to purchase your first home, or someday down the road when you're deciding to build a new home. what do you want to think about when you're making those purchases, because they, you know, will have an impact on whether or not your house remains safe in the event of a wildfire. And so with that, I'm going to see if there are any last minute questions that people have. The take-home message here, I think at this point I've made fairly clear, which is we need to make sure that the understories are not being allowed to grow to the point where they become a hazard in and of themselves. And so wildfire management in the past emphasized the idea of never letting anything burn, but the consequence of this is that we have produced forests that are highly flammable, and the fires that can result from these highly flammable forests are in many cases significantly worse than if we had allowed the forest to burn naturally when it was supposed to, and on that 50-year cycle of wildfire initiation in Southern California. So does anybody have any questions? Okay, with that said, if you have any questions, post it on Piazza. I'll see if I can try to answer them. And this recording will be put up around 1 o'clock, okay? You take care.